Hello everyone. Today I'm going to present CryptGPU, fast privacy-preserving machine learning on the GPU. This is joint work with Brian Knott, Yuan Tian, and David Wu. Machine learning has been widely studied in the academia and widely adopted in the industry in the past decade. The growing amount of data needed for a machine learning model also raises data privacy concern, therefore arising the need for privacy-preserving machine learning. For example, in the case of privacy-preserving machine learning inference, multiple hospitals hold a proprietary model for disease diagnosis, and there's a patient who holds a sensitive medical image and wants to determine the disease he has. The patient would send the medical image to the machine learning model, and the machine learning model will output a disease diagnosis. In order for machine learning inference to be private, we require that, first, hospitals should not learn about the patient's medical data, and second, the patient should not learn about the weights of the machine learning model. Similarly, in the case of privacy-preserving machine learning training, multiple hospitals may want to train their proprietary model for disease diagnosis. So the patient will send his medical image to the machine learning model. The model will output a training loss instead of a disease diagnosis. This training loss is then backpropagated through the model to update the model weights. Similarly, we require that hospitals should not learn about the patient's medical data, and the patient should not learn about the weights of the machine learning model. Note that privacy-preserving machine learning training is a much more challenging task than privacy-preserving inference, because first, input data are usually trained in batches of hundreds and even thousands of images. And second, there is an extra backpropagation step to update the model weights. Therefore, privacy-preserving training is much more computationally demanding than privacy-preserving inference. Both privacy-preserving machine learning and inference can be achieved via secure multi-party computation. In our work, we considered the following threat model for secure multi-party computation. We consider a three-party semi-honest security with honest majority model, where honest majority means that we allow a single semi-honest party for corruption, and semi-honest means that corrupt parties will follow the protocol but will try to gather information out of the protocol. One of the major tasks in machine learning and privacy-preserving machine learning is image classification. In the beginning, image classification is operated on small datasets such as MNIST, which has 60,000 images, and on small networks such as LaNet, which has a couple of layers. With the advance in computational powers, image classification has shifted to large datasets such as ImageNet, which has over 1 million images containing 1,000 classes, and on models such as ResNet, which has up to 200 layers. However, most of the work in privacy-preserving machine learning has been restricted to small datasets and small models. Not until recently, there are several works that try to extend privacy-preserving machine learning to large datasets and large models. These are Delphi, CryptFlow, and Falcon. And Falcon additionally supports private training. However, despite the recent advance, there is still a significant performance gap between privacy-preserving machine learning and plaintext machine learning. For example, in the case of private inference, the state-of-the-art work CryptFlow has a 23,000x gap compared to plaintext inference. And in private training, the state-of-the-art work Falcon has a 42,000x gap compared to plaintext training. Therefore, there is still a significant performance gap between plaintext and private machine learning. To make privacy-preserving machine learning practical, our main challenge is scalability. So how do we reduce this gap in privacy-preserving machine learning? Previously, when the datasets and models are small, communications of MPC protocols is the major bottleneck. Therefore, it would make sense to design more communication-efficient protocols for linear and nonlinear operations in machine learning. Many of the prior work has taken this approach. However, as we scale to large datasets and models, computations of machine learning models becomes a major bottleneck. We could leverage hardware accelerations such as GPU accelerations to speed up computations of machine learning models. Prior work such as Delphi has considered this approach. GPU acceleration is extremely important for machine learning. Take plaintext machine learning, for example. If we want to train ResNets on ImageNet on a single CPU, it would take over a year to train. However, on a single GPU, it would take only roughly a week to train. If for plaintext machine learning we need GPU in order to train a model, so it is for privacy-preserving machine learning. In fact, we observe from the state-of-the-art privacy-preserving training work Falcon, we observe that 98% of Falcon's training time comes from computing linear layers. To sum up, scalability is the biggest challenge in privacy-preserving machine learning, and linear layer is our main performance bottleneck. GPU can significantly accelerate computations of linear layers. Therefore, we need GPU acceleration for privacy-preserving machine learning. However, it is not that easy to directly support GPU for privacy-preserving machine learning. Plaintext machine learning performs GPU computation by invoking CUDA kernels. And plaintext machine learning uses floating point numbers for computation. However, MPC protocols operate on fixed point arithmetic, which require us to convert a floating point number into a fixed point representation represented by a 32 or 64-bit integer. However, there is no CUDA kernel supported for computation over 32 or 64-bit integer types. Therefore, we will need to support CUDA for fixed point arithmetic. We present our system CryptGPU, which supports end-to-end private training and inference on GPU. Our system supports private inference and training in a three-party semi-honest setting, and we keep all of our computations on the GPU. We've done a systematic evaluations of GPU-based multi-party computation and observed that both linear and nonlinear operations benefit from GPU acceleration. We built our work on top of PyTorch, the state-of-the-art machine learning framework, and Crypt10, a privacy-preserving machine learning framework built on top of PyTorch. Overall, our system shows a 2.5 to 3.7x improvement over CryptFlow and Falcon on private inference, and a 7 to 36x improvement over Falcon on private training. Our system design can be mainly summarized into three components. First, we use replicated secret sharing as our basic building block. Second, we design mechanisms to embed fixed point arithmetic into CUDA's floating point computation. And third, we develop GPU-friendly protocols for nonlinear operations. First, we use replicated secret sharing as our basic building block. Replicated secret sharing is a type of additive secret sharing, where multiple parties that hold its own secret shares sends its own secret share to the neighboring parties. After replicated secret sharing, each party will hold a 2 out of 3 secret shares. Replicated secret sharing supports addition and multiplication, and it is an efficient building block for a three-party computation. Second, we go over how we perform integer operations using floating point arithmetic. We rely on the following two properties. First, exact computations for small values. Namely, a 64-bit floating point values has 52 bits of precision, which means that it can represent all integers between range -2 to the 52 to 2 to the 52. For integers AB in range -2 to the 26 to -2 to 2 to the 26, their product AB can be represented directly as floating point values without any loss of precision. Apparently, for 32 or 64-bit integers required for multi-party computation, their product cannot be represented directly as floating point values without any loss of precision. We therefore need the second property, which is bilinearity. Bilinearity simply says products of two integers a and b can be broken down into products of smaller integers a1 plus a2 times b1 plus b2. Using this idea, we can convert product of large integers such as 32 or 64-bit integers into sums of product of small integers such as 16-bit integers that can be whose products can be directly represented as floating point values without any loss. This mechanism directly generalizes the operations on matrices. And based upon this mechanism, we develop a module called CUDA long tensor in our system as an abstraction. Finally, we go over the principle of our GPU-friendly protocol design. GPU is optimized for parallel processing of simple operations. For example, component-wise operations such as matrix addition and multiplication are fast, whereas operations with lots of conditional statements are slow. Therefore, we will want to design protocols suited for parallel processing. For example, for private division, we could use a Garble circuit to compute private division, but Garble circuit is less suited for GPU parallelism. We therefore use approximation-based method to compute private division. Similarly, in the case of exponentiation, we approximate exponentiation using a limit-based approach, which turns exponentiation into a sequence of multiplication that is suited for GPU parallelism. For a detailed description of our protocols, please refer to our paper. We've done a systematic evaluation of the performance of our system and compare it with some of the prior work. In the case of private inference, we compare with Falcon and CryptFlow. On small datasets and models, where communication is the bottleneck, GPU acceleration does not bring much benefit, and our system is slower than Falcon on LeNet and MNIST. However, as we scale to larger models and datasets, we begin to see the advantage of GPU acceleration. On VG16 on Tiny ImageNet, we observe a 3.7x improvement. Compared to CryptFlow, we see a 2.5x improvements on ResNet. Please refer to our paper for the full measurement details. In the case of private training, we compare with the state-of-the-art result Falcon. We found that on small datasets and models, CryptGPU has a 7x speedup. And on large datasets and models such as AlexNet on Tiny ImageNet, CryptGPU has a 36x speedup. Overall, we see a 7x to 36x improvement over Falcon on private training. Finally, we run a micro benchmarks comparing the performance of MPC protocols on GPU versus on CPU. For private convolution, running the protocol on GPU is 100x faster than on CPU. And for private ReLU, running the protocol on GPU is 10x faster than on CPU. Our micro benchmark shows that both linear and nonlinear operations benefits from GPU parallelism. To sum up, we present a system that supports end-to-end private training and inference on the GPU. Our system improves inference efficiency by 2.5 to 3.7x and training efficiency by 7x to 36x compared to prior work. Our results shows that GPU can significantly accelerate bottlenecks in linear layers. CryptGPU currently only supports computations on a single GPU. To further scale the system up, we need to support multiple GPUs. Also, it would be good to design more efficient multi-party computation protocols that better leverage GPU parallelism. Thank you.